This project was inspired by a well-loved 2D game, Pac-Man. We have two players, one acting as a ghost and one acting as a Pac-Man, both represented by mini robot cars. These cars are navigated using remote controllers that wirelessly, yes, wirelessly, move the cars forward, backward, turning left, or turning right via Bluetooth. And the aim for this game is for the Pac-Man to get to the other end of the maze without being tagged by the ghost. But can these four dedicated students pull this off? Stay tuned to find out.
We used lasers and photoresistors as the tagging mechanism between the two robots. We attached two lasers to either end of the ghost robot and two large photoresistors to either end of the Pac-Man robot. When the ghost robot got close enough to the Pac-Man robot, the photoresistors on the Pac-Man would sense the light from the ghost's lasers and would then turn on a NeoPixel also attached to the Pac-Man robot, which signaled that the player had been tagged. One of the concerns we had while designing the tagging mechanism was that ambient light would cause the NeoPixels to turn on without the player actually getting tagged. We were also worried that the surface of the photoresistors were too small and would be unable to pick up the laser's light. We decided to 3D print covers to go over the robots, which had small openings oriented so that overhead light would be blocked out, but light from the lasers would easily be picked up by the photoresistors. Another challenge we faced while implementing the tagging mechanism was incorporating the Arduino code for photoresistors and NeoPixel with the robot's motor control code so that both circuits would function simultaneously.
Our setup involves controlling the direction of the motor via Bluetooth, using two sides, side A and side B. Side A is responsible for receiving and handling the motor signals and translating them into movement. To set up Bluetooth, we initialized the BLE library and added characteristics to represent different motor directions. Each direction is controlled by a unique BLE characteristic, which enables our controller on side B to send commands to side A. These commands are mapped to the following characteristics: the forward motor state, backward motor state, left motor state, and right motor state for moving forward, backward, left, right, respectively. Each of these characteristics has a unique identifier and allows write access so that our remote controller can update them. With the Bluetooth setup complete, the next step is controlling the motors. We defined 4 motor control pins, A in 1, A in 2, B in 1, and B in 2, and set them up as outputs. We also have a loop function that constantly listens for commands received through the BLE characteristics. And so here is how the control works. If the user inside B presses the forward direction button, it causes the forward motor state characteristic to be set to 1, which means that the remote controller wants to move the motors forward. So we switch the pins A in 1 and B in 2 to high and A in 2 and B in 1 to low to rotate the wheels in the forward direction. If we want to move backward, we do the opposite. A in 1 and B in 2 are set low, while A in 2 and B in 1 go high. And if we want to turn left or right, we rotate one motor in one direction while reversing the other, allowing the vehicle to pivot.
Next, we will go into our Side B circuit and code. Side B corresponds to the controller circuit, in which we had a total of 4 push buttons connected to the Arduino Nano 33 BLE board. To power the circuit, we use either wired connections from the BLE board to a laptop, or a battery pack directly powering the breadboard, which made the controller completely wireless. While the controller circuit itself was fairly simple, the magic behind our wireless controller happened in our code. The Side B code for both the Ghost and Pac-Man robots was identical, as we wanted the logic and functions to be the same for both. In this code, we first assigned distinct pins on the BLE board to the value of each push button. Then, using the Bluetooth capacities of the BLE board, we established unique identifiers for each of the push button values that were being transmitted to the corresponding Side A circuits. Once the wireless communication was established, our code had the BLE board read the value of each button, update if the reading had changed, and communicate any update to the Side A circuit. This allowed us to wirelessly control the motors of the corresponding robot.